Hello, everybody. My name is Mohammed Saad Naeem, and today I'll be presenting what we've done in my thesis so far on bootstrapping supergravitons using machine learning. And my supervisor is Simon Karen Hewitt. So before we move on to gravitons, let's start off from what we know. We ask the question, what happens when light interacts? So we know from the double slit experiment that light behaves as a wave, but if you zoom into that wave, it's composed of photons. And so over here, we ask the question, what happens when photons interact? At low energy, if you, for example, you flash two flashlights at each other, what happens? So take a time to think about that. And actually, nothing happens, right? The light just passes through each other. But at high energies, approximately at 500 kilo electron volts, the photons, they emit a positron and a electron pair, and they scatter. So similarly, we know that gravitons are made up of gravitational waves. Sorry, gravity is made up of gravitational waves, which was proven experimentally. And if you zoom into that waves, it's composed of these hypothetical particles called gravitons. And if you're unfamiliar with the Feynman diagram, it's basically a way of visualizing scattering processes. So over here, as time goes on, this graviton and this graviton come in and they exchange some particle, which for gravitons we have no idea um, those look like. But some interaction happens and they scatter. Okay. And what we're trying to find is this: what sort of interactions happens over here. And we know that from different theories such as string theory and string ADS CFD, that they're basically toy models we're using to build up mathematical tools to get a better understanding what happens at 4 dimensions. But so far, we don't have conclusive results. We don't have a theory of everything. So that's our aim of this project. We go back to the basics and we say that this method is known as bootstrapping, where you use conservation laws to tackle the problem and narrow down what your allowed region can be. So what are the constraints that we want? So the first one is energy and momentum conservation, which is always nice to have. The second one, a bit more subtler thing, is causality. So we have two massless particles, gravitons, which are massless particles, and they have spin too, right? So they're approaching each other, and whatever interaction happens, they're gonna be slowed down, right? They can't be sped up, basically. If you've got two detectors over here, they can't be. If there exists a scattering interaction, they can be only slowed down. And that's what Kramer's chronic and crossing symmetry encodes. I won't go into too much detail, but basically what Kramer's chronic is a result taken from quantum optics, where it's a theorem which dictates how light propagates through material. And basically, two gravitons can be thought of as one graviton passing through another material. So that's a very important result. Another one is crossing symmetry. It basically relates how time is encoded into our results. I'll talk a bit more about it when I'm talking about the loss function. And finally, the probability of the interaction happening is between 0 and 1. So we know that the function which describes the interaction is encoded, it has values between 0 and 1. So using all these constraints, we ask the question, what can super graviton-graviton scattering look like if it satisfied all these constraints? Notice that I use the word super here because by super basic, so gravitons can be polarized in different ways, right? And if you use super gravitons, you can basically treat them as a scalar by using symmetry conditions. But this is obviously not what happens in real life, but it simplifies a lot of our constraints and the number of constraints we use. So what we present is neural networks to understand this function f of j on m, where j is the spin and m is the center of mass energy. And like a function of any two variables, we can use various polynomial approximations to it, like a related work of Pedro et al., who did exactly that. But we propose that neural networks would be a good approximation of this as well, because we know from the universal approximation theorem that neural networks can represent any continuous function. And also because we're not restricting ourselves to a polynomial, neural networks can learn like non-polynomial functions as well. And also, if you, so we know that a lot of time is spent by physicists on learning one specific interaction, but if we have a neural network that's working on one sort of interaction, we can actually increase it to different interactions, such as the number of gravitons and the number of interactions with other particles as well. So that's why we chose neural networks. And our inspiration was taken from the fact that machine learning has been successfully used in string theory and quantum field theory. And our novelty is that machine learning hasn't been used to model unknown interactions. And as far as we know, we are the first ones to use neural networks in quantum scattering. This is also pretty exciting because this the theory of gravity is unknown. So trying to model this, and we hope that we can eventually bound how, whoops, we can bound how much a theory of quantum gravity can differ from general relativity. So over here we have a f, which is a basis of function that describes interaction. And this entire diagram is equivalent to m, which is the amplitude scattering amplitude. And it's composed of two functions over here. It's the kernel of S and T and J and M. J and M I've already introduced as spin and center mass. S and T are basically Mandelstam variables, which relate the four momenta of these particles. And as you see, it's multiplied by this function f, which is unknown, and that's what we're trying to find. So what are neural networks? A very brief introduction would be you input X, your input data, it does some computation and it outputs Y. And our objective is to learn parameters such that it minimizes the loss function. What's the loss function? It's basically a function that tells how good or bad your prediction is. And we're trying to minimize that, which means we're trying to make the prediction very close to the original set of Ys that we have. This is supervised learning, very brief. Our input is J and M, the spin and the energy that we're using, and then our output is F. And basically, we use that output. We make a loss function such that it minimizes those constraints, and then we hope that it will converge. So there are many flavors to do this. One is gradient descent. It's a very old and widely used method where you initialize on a random point, and using small step sizes, while it's not converged, you compute the estimate of the derivative of the loss function, and then you update your theta. So hopefully you hope that it will converge to a nice point. What's the aim of neural networks is that when you introduce new data, it neither does underfitting or overfitting. It's made well enough that it like fits it quite well. So our loss function, our neural network is quite standard. The only difference is our loss function and how we encode our physics problem into it. And we spend a good amount of time analyzing our physics problem and then decoding into a physics computational one. And over here, we see that we made our loss function such that it encodes all the constraints. So the first constraint is the cosine symmetry. And like I said before, it talks about how time is encoded into our equation. So over here, we see that the interaction is happening where time flows in this direction and the gravitons come and interact. But this interaction is similar to this one given by this diagram, where time flows in this direction, the x direction, right? And so we can think about how interactions happen in all 360 angles and 360 degrees. And those interactions would all be similar. And what we want is that those all converge. Those are all equivalent. Another thing that we want is that because, so we know that general relativity works at high energy quite well, and we have various quantum theories that work quite well at low energies. But what we want is theory that works well on all scales. So over here, we're learning the high scale, and we wanted to converge with the low scale term over here, which is given by 8 pi c. And some of you might recognize that as the relativistic term in the low energy expansion. And this last term over here is G naught, which is the correction to how much a theory of quantum gravity can differ from general relativity. And we're trying to maximize this. So here are our results. So as we can see, this basically plots our prediction interaction F, and we can see that this model predicts that the lower spin particles have a higher chance of being a higher contribution in this interaction, and the high spin ones have lesser contribution. And this makes physical sense, right? Because we know that most of the particles in our standard model have low spin. For example, photons have spin 0, fermions have spin 1/2, bosons have spin 0 or 1, and these gravitons have spin 2, right? But why, you might ask the question, why high spin at all? Why aren't those all 0? And it's because F itself could be composed of different particles, right? So it could be a composite particle. So that is a bit non-trivial situation happening there. And also the relation with energy, we see that the higher the energy, it is less likely for F to be a high energy particle. That's because the two interacting particles are gravitons, which are massless. So there's not a lot of energy they can give off. So right now, the problem that we're facing is that even for the same parameters, it's converging to a different result, as we can see by these different plots over here. So what are some parameters that we played with? First of all, there's alpha and beta, and these say how much contribution do these terms have in the loss function. So obviously, if you increase alpha and beta, the loss function will give more attention to these terms. And we basically made a table of all the permutations of alpha and beta and saw that for which values of alpha and beta did this loss function converge most conveniently. Then there's also the number of epochs you can use, which is the number of times this loop runs. It's the technical term for that is epoch. So we're using 15,000, but it takes quite a time, but we can definitely increase that. Another bit trickier thing that's happening is the initial conditions, which is why these things are converging to, these graphs are converging to different results. And that's the thing we're struggling with. Even with this, with same parameters, even a slight change in the initial conditions leads to different results. And we actually decompose our loss function, which we're getting on the order of about 10 to the 5, which is a bit bad. But most of the contribution is from the crossing symmetry part over here. So we saw that that 10 to the 5, 10 raised to the power 5, our model learned these functions quite well, these terms, but it's having trouble figuring out a function that is symmetrically, crossingly symmetric. So what can we do to improve that in the next month is we could use a better validation set. We could also, instead of using random weights, we can see that at the end of the model prediction, we can see where the weight lies, right? And then we can use those as the initial weights and then use the learning rate as very small so that it doesn't diverge very quickly. In conclusion, we have demonstrated quite successfully that this proves a proof of concept where, yes, indeed, you can learn neural networks on quantifying quantum interactions and scattering. And we are getting physically reasonable results. So that's pretty good. We've also, we've yet to, like I said, we've yet to capture crossing symmetry. But like that perhaps is in the tuning the hyperparameters itself. But once we've done that, there's quite a lot of scope to this because we could add more particles or gravitons in the scattering. So instead of 2 to 2 scattering, we could do like add as many as we want. We could also see how gravitons interacts with other particles. So we can introduce other particles with different masses and spins in this interaction, and we can use more realistic non-supergravitons. So thank you for your time.